Okay, hi everyone. My name is Annie Martin. I'm a project officer for the Operational Space Medicine Group at the Canadian Space Agency. And today I'll talk to you about, astronauts held during exploration class mission, more specifically the ISS and future deep space mission. And I will also spend some time talking about biomonitoring technologies. Okay, excuse me, I had some issue with finding the next button. But first of all, the Canadian Space Agency, that I will now refer to as the CSA, is located in Saint-Hubert near Montreal. And the CSA is responsible for advancing knowledge of space through science and using its discoveries for the good of Canadians and all humanity. So Canada is a spacefaring nation with a rich history of achievement in space. And, Canada was the third nation in space in 1962. And since then, there was, numerous successes, such as our flagship program, like the robotic arm on the International Space Station, as well as the RadarSat family of space-based radar, as well as our astronauts corps. So human space exploration includes a tremendous numbers of accomplishments throughout the past decade, from the first man on the moon to the construction of the International Space Station. So the ISS is one of the biggest engineering success in the history of mankind and is certainly a model of international collaboration. So one of Canada's main contribution on the International Space Station is certainly the Canadarm, which you can see on the picture on the slide. There is currently 4 active Canadian astronauts. In the picture, in the bottom of the picture from the left to the right, we have Josh, then Jenny, David, and Jeremy. David Saint-Jacques will be the next Canadian astronaut to fly to the International Space Station. So he is scheduled to, his launch is scheduled for December later this year, and he will spend about 5 to 6 months on board the International Space Station. So the ISS is certainly paving the way to future human exploration while advancing scientific research and technology development, as well as inspiring all generations. So first of all, I will tell you a little bit more about what it is to fly in space. Because designing the next technology for future deep space mission to the moon, Mars, and beyond, it's important to look at what we know now, and the International Space Station and all the experiment on board has certainly helped us to better understand, the impact of microgravity, as well as how to live and work in space. So first of all, a mission start with a launch. So what you can see on the picture is the Russian rocket with the Soyuz capsule, where the astronauts are located. So it is quite a ride for astronauts, but also for the equipment that is inside the capsule. So any technology that fly on board the International Space Station have to survive the launch. So and the launch include a lot of vibration, and the launch is equal to approximately 4 to 5 Gs. So once, on this picture, so you can see that the Soyuz vehicle is quite crowded. So there's not much space left in the vehicle. You'll excuse me 2 seconds. So so there's limited supply that can go on board the ISS using the crew capsule, but there are also some other capsule, like the Dragon capsule by SpaceX, which is providing any equipment or item necessary to resupply the International Space Station. So once the astronauts are in space, they have a very busy schedule, so they will spend most of their time, maintaining the International Space Station, as well as conducting research experiment and doing some outreach activities. So the International Space Station is a unique laboratory where we get to advance, knowledge on a variety of topics, and especially how gravity and once we remove the gravity, effect on the human body, on living organism, materials, processes, and so on. So the astronaut currently spend approximately 6 months on board the International Space Station. Before the space shuttle retired, astronauts were able to do shorter mission of approximately 2 weeks. But now, there's always a crew of 6 astronauts on board the space station, and each mission lasts approximately 6 months. So when coming back, there is also a 4 to 5 G load on the astronaut because of the impact. So you can see on the top left pictures, the Soyuz and the opened parachute. So if the return is phenomenal, so if it has a ballistic re-entry, then it can go up to 8 to 9 G, so which is relatively important for the crew. So you can also see on the picture that there's a team of people waiting for the astronaut to come back, and you can see that they are in a sitting position. So one thing that is important is that when the astronauts are in space, their body adapt to the microgravity environment, and so then in terms of blood volume, the cardiac capacity reduce a little bit, because when in space it's like being lying down in a bed, so your body doesn't have to fight gravity, so that it does not require, for example, the same amount of blood volume or the same strength to distribute the volume, the blood in all the body. So when the astronaut come back to Earth, then the gravity will pull all the blood in the feet. So then the body have to and the heart have to work harder to bring back the blood to the brain. So that's why they are usually sitting down, and they usually cannot stand for a long period of time. So we call it orthostatic intolerance when they come back to Earth. But fortunately, it's something that the body readapt quite rapidly, and then the astronauts are quite rapidly able to walk around and stand still. So in order to better understand, what we need to medically support astronauts during spaceflight, we need to understand the hazard and the risk of being in space. So I present you some of the main risks for astronauts. So first of all, as I mentioned before, there are high accelerations during launch and landing, which is particularly a high risk time. And there is also numerous physiological effects of the microgravity on the human body, muscle atrophy and bone loss being some of the most important one. In addition to that, background noise can be important in the spacecraft, which can cause significant physiological stress. There can be some impact to sleep, and it could also cause some hearing damage. Also, the work and life schedule, as I mentioned earlier, is busy for the astronaut, but there's also the fact that it's dictated by others. So the crew has to follow a clear procedure, and their daily schedule is decided by the people on the ground. So it does create some performance pressure. Another important aspect is the enclosed atmosphere and environment. So there is a risk of decompression. Let's say there's a micrometeorite that hit the space station. There is also a risk of fire if ammonia leak. The spacecraft is also an environment with a higher concentration of CO2 if we compare to the ground here. So it could affect, the health of astronaut if exposed to some hazardous substance. So finally, the last three categories of risk I'm going to talk to you about. So there is a higher exposure to radiation, once on the International Space Station, so which could increase the risk of cancer. So it is estimated that for a 6-month mission, the dose of radiation is equivalent to, a lifetime dose of someone on Earth. Which is a lot. And if we think of a Mars mission, the equivalent will be like 1,000 times the Earth average background radiation for a mission to Mars. So this is an important showstopper for Mars mission. So we need to make sure we know how to protect the astronauts from the radiation to make sure that when they come back relatively healthy. Another important aspect is all the psychological stress caused by the isolation. So being away from family and friends is certainly a source of stress. When you don't know what's happening on the ground with your family and being so far, it is stressful. And this same kind of situation happen with people that are in Antarctica. So lots of data, lots of study have shown the impact of isolation, and there are certainly some mitigation strategies for astronauts who are going in space for a long period of time. And finally, there are also the challenges of delivering healthcare to astronauts, such as the limited medical infrastructure and the limited capabilities of medical evacuation. So when we looked at the Soyuz picture, it's very crowded. So let's say the astronaut is sick, has an IV line, there is no way that this is going in the capsule to come back. So there are some limitation in terms of medical evacuation. So these are hazards as they relate to the spaceflight environment. But in addition to that, crews can get sick just like you and me can get sick. So the crew need to be prepared for different situation and different potential medical condition. So medical care is an important aspect of human spaceflight since we want to make sure that the astronauts are healthy while performing their job in space, so to ensure success of the mission. And we also want to make sure that they can come back, as healthy as possible, even though we know that, the microgravity will affect the human body. So considering the risk and the medical capabilities in space, one important thing is that the main mitigation strategy is prevention. So prevention is done through a rigorous selection process to select astronauts. There are also some annual examination as well as pre-flight, in-flight, and post-flight medical testing to ensure that the astronaut is healthy. In terms of medical support of astronaut, during the mission, so in-flight medical support, the person responsible for the astronaut is the flight surgeon, and the flight surgeon is located on the ground in mission control or in his or her agency. So for example, when a Canadian astronaut is flying, our flight surgeon will sometimes go to Houston for in mission control, or he can do the private medical conference from his office at the CSA. There are also some health and behavioral performance support to assess cognitive and psychological health of the astronaut. There are some nutrition and fitness assessment, so they have to do a periodic fitness evaluation to look at the cardiovascular capacity. There's vision and eye testing. In terms of real-time monitoring, a lot of people would think that the astronauts are constantly being monitored in space to make sure that we understand, what's going on with their body and their vital signs. But actually, the astronauts are not being monitored at all. Well, in some circumstances they are monitored. So for example, when they do their periodic fitness evaluation, they are wearing a heart rate monitor. And when they do extravehicular activities, so when they go out of the station to do some either some repair or to work on the external structure of the International Space Station, then they are monitored to just to make sure that in terms of heart rate, fatigue, hydration, since the extravehicular activity, which we also call EVA, are very intense activity. That's why they are monitored. It's one of the most risky activity of an astronaut. But other than that, they will be monitored if it's part of a research experiment. But in other circumstances, they will not be monitored. And finally, in terms of in-flight medical support, medical condition will be managed as they occur, usually with in consultation with the flight surgeon on the ground and with the crew medical officer in space. So even though the main person responsible for medical care is on the ground, there is an astronaut with the role of the crew medical officer. So the crew medical officer can be a physician or another astronaut, with a certain level of training. So there is limited training of astronaut with the role of the crew medical officer. So sorry, I'm skipping slides. So there's a limited medical training. So usually approximately 45 hours of training. But for example, for our Canadian astronaut flying to the space station, David Saint-Jacques, he's also a physician, so he will play the role of the crew medical officer. So amongst the task of the crew medical officer, he will assist the crew if there's any assistance required for any medical related activities or requests that may have. There is also limited infrastructure and equipment. So as you can see in the pictures on the bottom, in order to define what's on the space station, the NASA and the international partners look at what are the risks, the risk of occurrence, the impact, and then they identify, what is the necessary equipment. If something happened that they were not prepared for, let's say if there's an appendicitis, which they cannot predict its occurrence, then the crew would be treated with medication, and if it doesn't work, then it would be there will be a medevac back to the ground. So I'll just go back one slide, because I skipped that one. So I presented you, all the risk, the main risk of flying in space, and the exercise, is the primary in-flight countermeasure for cardiovascular deconditioning, as well as bone demineralization and muscle atrophy. So you can see in the bottom image, on the slide. On the left, there's the CVIS, so the cycle ergometers. Then you have the treadmill, and on the right hand side, you have the advanced resistive exercise device. Nutrition is also an important component, and it is required to reveal the full benefits of exercise and also to enable a higher exercise intensity. So their daily energy intake is also carefully planned by the nutrition specialist to ensure that they have all the nutrients and the calories required for them to complete their task. So another important aspect of human spaceflight is that in order to improve our prevention methods and our understanding of the effect of microgravity and of spaceflight on the human body, there are life sciences experiments that are conducted on board the space station. So just to give you a few examples of the Canadian life science experiments, there is vascular echo, which studies the effect of weightlessness on astronauts' blood vessels and arts on board the ISS. There is also marrow, which is a study on the bone marrow, so the spongy tissue inside the bones and the blood cell it produces, and to look at how it changes in space. Also, Radiant 2 involves bubble detectors, to help quantify neutron radiation inside the International Space Station. And the last example, there's the experiment At Home in Space, which examines how astronauts from all over the world make the space station feel like home, far from friends and family, in such a stressful environment. Canada will also soon deliver 2 life science research systems on board the International Space Station. So on the top you have the bioanalyzer, which will enable testing of different body fluids such as blood, saliva, urine, for a biomedical analysis. So it's the prime contractor for that project is Honeywell, and it's supported by Atlantic Microscience, Sensorial, and Zyphos Technologies. Another interesting project, the other life science research system, which will be launched soon, I think in November, is Biomonitor, which is a wearable technology to monitor and record vital signs. And I'll tell you more about it in a few slides. So this is a project led by Kari Technologies and in support from Calm Technologies as well as Zyphos Technologies. So before moving on to deep space mission, one last aspect I wanted to talk to you about is the space analog. So access to space is limited, and it's very competitive, and it's difficult to get access to the International Space Station. So there are some analog on the ground that mimic some characteristic of space flight. So there are bed rests, remote and isolated sites, underwater laboratories, and some isolation study, which is, if you look at the picture, on the right hand side, it's the NASA Human Exploration Research Analog, HERA, which simulate like a Martian or a lunar habitat, and there's a crew that will live there for 30 to 45 days with activities that are like what astronaut would do, and then they are monitored with lots of sensors. There's lots of tests and surveys, and they are studying the effect of isolation. So what's next after the ISS? So in terms of the next steps in human space exploration, the next mission will be the cislunar mission, so on the Lagrange point in the vicinity of the moon. Then they are planned to go back to the surface of the moon, and eventually to be able to send humans to Mars. So there's a paradigm shift, for deep space mission when it comes to medical care delivery. So the paradigm shift is from Earth reliant, like on ISS the astronaut rely on what the ground would dictate them to do, and the shift goes to Earth independent for Mars mission. So in for medical support, it's like we're moving from the telemedicine paradigm to one of medical autonomy. So crew health and performance will have a significant impact on mission success and mission risk. So this is why we need to make sure that the crew remain healthy for the entire mission. And if we think of what we know about the effect of microgravity, we do know a lot, but there is still a lot of uncertainties in terms of, what is it to be on Mars, away from Earth, and for a prolonged period, because the Mars mission will be approximately a 3-year mission. Also, in addition to the long duration missions, there will be communication delay, which could be up to 40 minutes two ways. So by the time they say, Houston, we've got a problem, it could be too late. So that's why there will be a need for tools and technologies to increase the capability of the crew in terms of medical support. And because of the distance, there will be no emergency returns. So again, the use of technology and other treatment capabilities will be required to make sure that they can remain healthy and have a successful mission. So there will be a crew health and performance system on board that spacecraft for a Mars mission to make sure that the crew can take care of themselves, and for the health management of the crew. So that medical system will help maintain crew healthy with countermeasures, exercise, behavioral health, food, etc. The system will also be used to prevent, diagnose, test, and manage long-term health care. It will also support the crew to accomplish mission tasks and allow for medical autonomy and, in some time, telemedicine. So it's not all the medical condition that would require autonomy. For example, if there's a rash or a bruise, a picture can be sent to the ground, and the crew can wait for getting feedback from specialists on the ground. So so there would still be the possibility for a store and forward telemedicine paradigm. And one thing I want to add is, even if there's a lot of communication delays, I said up to 40 minutes two ways, there will be time of blackout, so no communication at all. So NASA is estimating a period of 2 weeks per year. So again, that's why the importance of autonomy is important to ensure the success of the mission. In terms of provision of medical care, the system will require multiple data to make sure that the crew is capable of managing their health. So, input from vital signs, imaging, also the environmental data, which can influence health of astronaut. Let's say, for example, the level of CO2 within the spacecraft. Also historic data and etc. There will also be a component of the system that will look at data integration and management to make sure that we can properly manage the data, store the data, retrieve the data for further analysis. Also some decision support tools. In period of blackout, the crew medical officer that will be on board will not be a specialist in everything. So if a medical condition comes up, having some tools to augment its capabilities will certainly help the crew medical officer in the decision-making process. So we think artificial intelligence, deep learning, all sort of decision support system that could help the crew medical officer. And finally, technologies and consumables and equipment for treatment will be required, as well as training. If the crew member needs to do a suturing procedure, maybe some refresher and some tools to train would be useful before doing the procedure. So now let's talk a little bit more about biomonitoring technology, since it's one of the main topic of this talk. So first, the CSA has been working on prototyping activities since, I would say, approximately 2012. So I've been involved with these projects since the beginning. So we've been working with Kari technology, since like I said, 2012. on a smart shirt. So you can see on the image, it's a wearable garment, with embedded with sensors. It's washable. It has a wireless communication. It allowed to monitor a certain number of physiological parameters, such as there's a 3-lead ECG. So it monitors heart rate, but also heart rate variability. There are some band for respiration, so we get the respiration rate, respiration volume, estimated minute ventilation as well. There is a sensor that goes on the forehead. So on the picture that you can see, it looks like a light, but it's actually just to show where the sensor is located. So it's to monitor oxygen saturation, and using oxygen saturation and the ECG, there we get the derived measure of systolic blood pressure. And there is also a sensor for skin temperature. So I don't know if you can see with the camera, but I brought one Astroskin, and you can see that there's textile sensor for the ECG with a skin temperature, and all the data is being recorded and stored in that box. Data is streamed using Bluetooth to a mobile device so that the crew can look at the data, but then the data can also be transferred to a server, in a data management system. So in addition to that, this smart garment, is part of the Biomonitor, the life science research system. As you can see in the image, which we also call the Astroskin, which is the name of the garment, but the name of the payload on board the International Space Station is called Biomonitor. So it has been qualified for flight. So there was some modification from the ground version of the equipment. There is also a commercial product called the Exoskin, which is extensively used, with athletes and for many research projects. So the launch of the Biomonitor is scheduled for November 2018, and it will be used on the International Space Station. So the various steps, before being allowed to use the system in space. So there is what we call a commissioning, which will occur early 2019. So for the commissioning, David Saint-Jacques will wear, the equipment. So he will wear the garment and for 48 hours. And then the company will look at the data to ensure, data quality and integrity. So then, if everything works well, it will become a life science research system that will be available for Canadian and also our international partners. So CSA has already done a call, an announcement of opportunities, and basically that's how it works for Canadian experiment on board the space station. So the CSA will have some calls for proposals, and then there will be a selection of experiment, and then the international partners would also be able to advise CSA of their interest to use the system, and they would be able, to use it. So the data that is collected on board the International Space Station using the Biomonitor, for a research project, the data is transferred to the ground, and then it goes to the researcher. So this is not data that is available to anybody. This is not public data. So any data that monitors the health of an astronaut is considered private medical data. So this device is not, the intention is not currently to use for operational, but we are currently investigating how we could use it for in an operational context. So for example, during exercise or other activities. And what will be interesting with that system is that, as I mentioned earlier, the astronauts are not being monitored in space. So this technology allow for a comfortable way of monitoring vital signs, since it's like a shirt. It's almost invisible to the astronaut, and it's one important thing that the astronaut, they don't want to feel like they are monitored all the time. So with all the cables or all different sensor on different part of the body. So with the garment, can be seamless, so they can do their everyday task, and then we can collect data to better understand what is it to be healthy in space, because as you know, we have the baseline on the ground, what is their healthy state, but then when they are in space, the body adapt to the space environment, and then they have a new baseline in space. So with such technology, it would be interesting to see what it is to be healthy in space, and that's a technology that can help us achieve that. So one of the many technology, I should say, that could help us in that. So, and another project that we have, it was with the same company. It was still using a competitive process, but they won that other contract, which is the on-astronaut wireless sensor system. So it's a prototype. So it's what we also call a patch system. So patch that stick on the surface of the skin, and then it continuously stream vital sign data to a server and to a mobile device. So the idea with that project was not to move away from from the smart shirt, because these two could be complementary technology. But the idea was to assess the capabilities of having wireless sensors that could be attached on the skin for a longer duration. So for example, the patches that we have can last 7 days on the skin, and then it's about looking at what data is accumulated, how can we manage, analyze the data, and maybe in certain circumstances the garment is a better option, but in other circumstances maybe the patch would be more appropriate. So it really helped us to better analyze the different option of biomonitoring technologies. So these patches, measure the same vital signs as the astroskin, and the reason is that these are the basic vital signs that a physician will want to look at. But in addition to that, we also have the galvanic skin response to assess, stress levels. And what's interesting is what is the future, because we are looking at the different ways to monitor vital signs continuously to accumulate data, and we know that this field advanced quite rapidly. We can think of the tattoo sensors, the tricorder from Star Trek, using imaging, at a distance that could measure the vital signs, measuring vital signs using, glasses or contact lenses. There is different new technologies that are emerging on the market, and we are very much interested in looking at, what is the state of the art and what will be the next generation. If we're going to Mars around, 2035 or so, there will be new technologies out there. So what is important for us, in terms of looking at those future technologies for space flight, and thinking specifically of biomonitoring technology. So it has to provide an essential capability, so to monitor health parameters that make sense for astronauts. So for example, on board the ISS, monitoring diabetes is not a priority. It's relatively healthy astronaut, but it may be necessary at some point to monitor the glucose level, just to look at the astronaut. But as you see, there are essential parameters that a physician would want to see, or specific data that would be required for having some analytic tools to help with the data analysis. It also needs to be robust. There's no technician on call, and especially for Mars with the context, and the concept of medical autonomy. It must also survive the launch, so it cannot be a fragile technology unless the packaging is really maximized to reduce as much as possible the vibration. It has to be automated as much as possible with little or no resupply, because resupply will be very much limited, almost impossible on the first Mars missions. Maybe when there will be a colony will be a different stories, but right now, if we think of a Mars mission, it will be without any resupply. It has to be safe and simple to operate and repair. One important aspect of technology flying in space is that there should not be any sharp edges, because as the equipment, they just float in space. It can be dangerous, so have to be careful with smart edges, and they do very rigorous testing with the equipment to verify if there's any sharp edges. And if we think also of the technology requirements, here's are pretty generic, but we have to think of how will the crew be using that technology. So it has to be non-invasive or minimally invasive, because in space blood will tend to float and go all over the place, so it's more it can be more problematic. Ideally, if it can assess multiple parameters to reduce the number of sensors, and it has to be suitable for different aspects of the astronaut schedule, so from sleep to daily work, exercise, extravehicular activities, and so on. Ideally, if they are wearable, portable, wireless, small, lightweight, not obtrusive, because they have to do, to complete the other tasks that they have to do. Plug and play, user friendly. When you think of a mission, the astronaut can be trained on a technology a year before the mission. So by the time it's going to be needed for the astronaut to use it, then it has to be as much user friendly as possible. Also, system scalability. So there will be first mission to the moon, to Mars. So if a system can be able to expand on its capability and incorporate new function, then that's better for a system, because we can then improve and increase it as we move forward. And I want to conclude with the terrestrial overlaps. So the investment that the Canadian Space Agency is making for biomedical technologies. What's important is that what we learn in space and what we develop for space is not only applicable to astronauts, but also has great potential for spillover benefit on Earth. So it can be the research, the procedures, or the technologies. It can support medical care delivery in remote and isolated communities, where their situation can be similar to human spaceflight, with limited access to medical specialties, limited access to medical infrastructures. The medevacs can be difficult, expensive, and sometimes delayed or almost impossible, for example during wintertime in the north of Canada. Also, industrial and military setting, they do have constraints that are similar to spaceflight. We think of home care, aging population, personalized medicine. These are all trends that we are observing here on Earth, that are very much similar of the vision for technology and health sciences for astronaut. So it's interesting to see how companies and researchers can have that dual approach of looking at challenges and issue for their market, or their research opportunities on the ground, but look at how they can apply those technologies and those research questions to astronauts to help advance our presence in space. Because now we're on the International Space Station, but we're preparing to go back to the moon and then to Mars, and potentially also asteroids. And when we look at the private sectors, how some companies in the United States are aggressive in terms of human space exploration. I think there's an exciting future for human spaceflight, and in terms of Canadian capabilities, there will also be good opportunities for Canada to join this adventure of human spaceflight. So who knows, maybe one of you will be one of the astronauts flying to Mars, or maybe you'll be part of a team in a company that will develop technologies for space. Now it's limited to the space agencies, but with the private sector, as I mentioned before, with space tourism, the opportunity will increase. So if you have any question, I left my email address, so don't hesitate to contact me. I'll be happy to answer your question. So I hope you enjoyed the presentation, and I wish you the best of luck for your studies and your future career. Thank you very much.